Where did we come from? Where are we going? These are age-old questions. From before the Greeks until now, people have been wondering. As discussed in episode 1, the Big Bang Theory is the popular explanation now of where we're going and where we came from. It all started with a bang. Well, there's another theory, and that's called the steady-state theory. That says that we never started anywhere and we're not going to ever end. Let's talk a little bit about the Big Bang Theory. The Big Bang Theory tells us a story about the universe. Its origin, it inflated very fast, faster than the speed of light. And it keeps on expanding, boom, boom, boom. And furthermore, this expansion will never end. It'll never end. And eventually, the universe just keeps going on, and pretty soon, it's gone. It totally dissipated. That makes me think of the song Dust in the Wind. I don't know if you've heard of it. It's probably 30 years old now. But the dust in the wind may be just all we are if we adhere to the Big Bang Theory. One simple, irrefutable fact gave rise to the Big Bang Theory, and that is the Cosmic Redshift. Light coming from stars at a great distance is shifted toward the red. It's like the sound of a train when it's going away from us. The sound gets lower. Essentially, the light that's coming from very distant galaxies gets lower, gets more toward the red. The redshift not only is getting lower the farther an object is away, like a galaxy or a star, but it seems to be getting bigger and bigger the farther it is away. This is a very strange circumstance. I think it's very hard to support. So let's start with the data. Let's start with the very original data. We can understand better what the redshift means. According to Hubble, the redshift corresponds roughly to distance. This is not something that we can disagree with. The real data gives this rough correlation. Here's the graph of some of Hubble's original data. The correlation between distance and the shift of the light toward the red. You can see that there is a very rough correlation. That's what that line through the graph means. But if you'll notice, the data points are scattered all over the graph, even though there's a rough trend toward the greater distance and the greater redshift. On the other hand, you have this cluster of galaxies. They're all spread all over the place. This is something that should call our attention to the fact that maybe there's something else happening. If stars are flying away, the assumption is in the derived model that there was a big bang or an explosion at that early time. That's how we got the Big Bang Theory. Based on the redshift interpretation, they say, the scientists say who support this, that the universe was started 13.7 billion years ago. On the other hand, we have some problems with the Big Bang Theory. We have some data that doesn't necessarily correspond to what you would expect if the universe expanded very fast. If there was a Big Bang, you can imagine an explosion. You know, maybe you've seen one of your friends put a firecracker underneath a bottle, and you go around and you look at the pieces that are left. They're big chunks, they're little chunks, and they're spread around, not necessarily randomly. This is a characteristic of explosions. The scientists have originally thought, well, if there was a Big Bang, the universe would be very clumpy and curvy, and there would be a lot of inconsistency. It wouldn't be the same in all directions. However, it is the same in all directions. So their conclusion was the universe had to expand very, very fast, much faster than the speed of light. Well, that's a problem, of course. With relativity, you can't do anything faster than the speed of light, right? So there's a contradiction there. The universe is very, very smooth to a very tiny fraction of a percent. Well, how could this be explained? This is a very difficult problem. So what they have come up with is the resulting fix is cosmic inflation. As if it all expanded out very fast, faster than the speed of light, and over just a few seconds. This is not good physics. On the other hand, there's another fix they have to deal with in the Big Bang model, and that is there's not enough matter seen to account for the motions of the galaxies and the stars that are predicted by the Big Bang theory. So what do they have to do? In order to make that part of the theory work, they had to invent dark matter. Dark matter is matter that you can't see by its light, you can't see by reflected light, and as a matter of fact, you can't detect in any way that we have at the moment using electromagnetic means, because after all, astronomers use telescopes, radio telescopes, and various forms of electromagnetic energy to understand what's happening in the universe, and dark matter cannot be seen, has not been detected. There's another problem. Suppose the mass in space slows down. Suppose it keeps slowing down. Well, that would be the natural thing that you would expect if there was such a thing as gravity and lots of extra dark matter. You would expect that as the expansion goes out, it expands and it expands. Eventually the gravity would sort of overcome and it might at least slow down or even start collapsing again. This is not seen. So what do you do about it? How could that possibly be? Well, another fix to the Big Bang theory is they had to add dark energy, which sounds like a contradiction to dark matter. So dark energy is some mysterious force in the universe that keeps it expanding, and not only expanding, but expanding faster and faster and faster. Now, is that a good fix? I don't know. Dark energy, just as dark matter, has not been detected yet. That's very strange. The entire theory of the Big Bang now depends on dark energy and dark matter. So there are so many contradictions in this Big Bang theory, I'm surprised it's so popular. But it is the theory du jour, the theory of today. Here we have the tree. I just put this tree in just to show you that it started out, the Big Bang theory, with an indisputable fact. That fact is there is a redshift, and it is greater the greater you look out into space. The more distant galaxies have a greater redshift than the closer ones. We have that seed which we can depend on, which is true, it's irrefutable. But then we have the primeval atom, dark matter, inflation, dark energy. None of these in our tree of cosmic theory, called the Big Bang, have been detected. So where does that leave us? That leaves us in a very odd position. We might question, if we were following the scientific method, the very fact that the Big Bang is true, because it depends on all of these characteristics that no one could detect or have detected. So, since none of these have been detected, we could chop down this tree. Too many contradictions. Let's find another hypothesis for the cosmology that has fewer contradictions. Infinity, an infinite universe, infinite in space and time. I'd like to demonstrate to you how this has fewer contradictions. The features of the infinite universe steady state theory, first of all, the redshift is not interpreted as a Doppler shift. That is, we don't interpret the light coming from these different galaxies as representing the galaxy's movement. The galaxies do move, and they do have red shifts and blue shifts according to their inherent motion. But the bulk of the redshift can be interpreted as something else. An alternative cause exists for that distant redshift. There are various possible causes. We know we get a redshift of light if light passes through a very dense gravity field. Certainly when light is leaving the sun, it is redshifted. We know this from studies of the sun. Light is redshifted as it leaves the sun. Light is also redshifted. It loses its energy if a photon is flying through space and it interacts with something like a molecule or an atom. If it grazes by that, it imparts a little energy to that atom, and the photon that's going on loses some of its energy. So one cause of this is called the Compton effect. This is fairly well known, well-established theory. Another way photons can lose energy is if they're passing through a plasma field. Plasma is another form of matter where it is totally ionized, and it turns out that space is filled with plasma, very high energy plasma, probably more than anybody realizes. I've read recently that plasma is a very natural and common feature in the universe. And if you have a photon traveling hundreds of millions of miles, they're going to be encountering plasma and other atoms. They're going to be going through electromagnetic fields. They're going to have a very rough trip on the way here. It's very possible, in fact, I think it's certain, that photons lose their energy from those causes. And if we look back at the graph that Hubble gave us, you'll notice how the returns, the redshifts that are the result of the redshifts that were taken off of the galaxies, that they're scattered all over the place. I'd like to suggest that photons on their way here lose their energy, and it's not just strictly a function of the distance. It's also the fact that it has these other fields to go through. And I'm not prepared at the moment to say which causes of the redshift are the most common, the most important. But I think the fact that there are so many different possible causes gives us the opportunity to say there are other causes for the redshift. And if we have this huge superstructure of the Big Bang that depends on the fact that the universe is expanding and then brings us all these other special fixes to make the Big Bang work, I think if we have one very simple explanation for the redshift, and that simple explanation gives us a universe that matches our physics otherwise, then I think this is a very good candidate for a theory that we can rely on. We can say the universe is infinite, and infinite in time and space, and we don't need a Big Bang theory. So where are we? Where are we with this? Let's sum up. The resulting alternative infinite universe gives us no point of origin, which could never be proved. It gives us no inflation, no dark matter, and no dark energy. It's the universe as we see it now. And we can say that it had no beginning and it will have no end. So, what do we get with our infinite universe? Remember in episode 1 I talked about I want my Star Trek universe. I want my Star Trek cosmology. Well, I think this gives us part of the Star Trek cosmology that I'm looking for, that we're looking for. Humanity doesn't end, it goes on forever. The universe is not flying apart. It's infinite. In fact, it's more infinite than we could possibly imagine. What advantage do we have in having this steady state infinite universe? Well, I'll tell you. There is more to the explanation for how we get to our Star Trek universe. What is holding us back is a few equations and some limited laboratory experiments. So stay tuned for episode 3, where an alternative to the limitations of the relativity theory are going to be overcome. Believe. Check out episode 3 and see if you really think that we can have our Star Trek universe?